All right, welcome back. This is a lecture on feature importance, Lasso, bridge regression, and elastic net. I'm Professor Wu, so let's get started. All right, so let's have a quick recap of the previous lecture, which we talked a little bit about this concept of bias and variance. So, bias is basically whether the average point of your predictions are on target. So, notice how this one here, even though the results are not very good, the average point is roughly around the center, and therefore this is a low bias. We also learned the definition of variance. And this led us into the idea of bias variance trade off, where when we are trying to improve our bias, so notice here, this line didn't do a very good job basically fitting this point. However, whenever we try to do a better job with a more complicated model like this one, we end up increasing the variation. Notice how there's a big bump here now. And you don't want these big bumps based on the bias variance trade off. Okay. So when we try to use a more complicated model to lower the bias to like hit this point, it increases our variance to something kind of too high. And when the variance is too high, we call this overfitting. That implies we use an overly complex model, which is not good. Okay. So today we're going to learn how to use complicated models. Let's use complicated models, but simultaneously minimize the variance. We call this process regularization. So, how does regularization work? When performing a regression, we aim to minimize the average square of the prediction error, right? So, this was what we were trying to do before. When we perform regularization, all we do is add an extra term here. So previously we were minimizing this. Now we're going to minimize an extra term. And this extra term is called a constraint. So we're basically adding a constraint. So the result of adding this constraint is such that if you add the right constraint, is that we can continue to use complicated models while minimizing the variation. And we can see this example here. We have the black line here, which is a linear model. Therefore, it's as simple as it gets. It has basically no variation. And the red lines here, the red line has a large bump here, which shows you that there's a good amount of variation. So the green line is the result of using this constraint. So what we did is the red line was the fifth order polynomial, which gave us a really big bump. However, if we combine the fifth order polynomial with the constraint, the result is the green line. Notice how it's still able to hit this point, which is what we are trying to do, and it's not increasing the variation by very much. So, in a sense, it created a really good compromise. Okay, so the idea of creating this compromise solution in green, it is called regularization. It is also called adding of constraints. So, why do we call this adding a constraint? Because we're adding a constraint, and depending on the constraint we add here, it results in different algorithms. And the three most common constraints are if you put the L1 norm of the weights, okay? And if you put an L1 norm, this is called a lasso. If you put an L2 norm, it is called a ridge regression. If you put an L1 norm and L2 norm, then this algorithm is called elastic net. So each one of them has different names. But underlying all these fancy names, it is really just the concept of adding a constraint. Depending on which constraint you pick, it became a different algorithm, and the researcher was able to publish a separate paper. So at this point, notice if we want to minimize this objective, we can simply take the derivative and run gradient descent on them. It turns out that for this one and for these ones, there are no closed form solutions. So without closed form solutions, your only alternative is to use gradient descent to solve it. Luckily, we spent a lot of time learning how to take the derivative of this and as well as derivative of this. So you should know how to take derivative of all these. Now, as a side note, sometimes you will see the regression objective with 1 over 2, and sometimes you will see 1 over n, right? And it turns out that when you solve the problem, the minimization problem, using 1 over 2 or 1 over n doesn't really matter. What matters is later on when you take the derivative, the size of the derivative will change a little bit. So just keep that in mind, that using 1 over 2 or 1 over n are two ways that like various people might write the regression objective. Okay, so at this point, I want you to pause the video and essentially find the derivative for all three functions. Okay, pause the video. I'm going to continue. So over here is the solution. Hopefully, you're able to do it. Now, why do we call them constraints? Well, let's think about it. If we are only trying to minimize the mean square error objective, then your solution is basically anywhere. However, notice how if we add a norm constraint, since this norm is always a positive value, if we have a very large weight, it kind of goes against the minimization. Therefore, it turns out that when you run gradient descent, the solutions you get is constrained to a subset of weights where the size of the weights are significantly smaller. Okay, because you want small weights that satisfy this rather than very large weights. Therefore, you're constraining the potential space that you can have to find a solution. Okay, the constraint essentially constrains the solution to smaller value of weights. All right, and sometimes we call this constraint also called the penalty term, because whatever weight you pick here, the larger the weight, the greater the penalty. Okay, so it penalizes solutions with large weights. Okay, now I want you to think of regularizers as essentially adding an extra constraint on the solution. And the constraint is an and statement. I want to achieve my regression objective and I want the weights to be as small as possible. Okay, so that's how you can picture the constraints. Now, we can add and fine tune additional power to these constraints by adding these constants in here. Lambda over here are just numbers, scalar values, they're not vectors. And by putting a very, very large lambda, you are basically telling the gradient descent that you really, really care about this constraint. Okay. Now, if you put a zero, basically you're saying you don't care about this constraint. In fact, the impact is zero. Okay, so you can essentially control how much you care about this constraint by controlling the value of lambda. Okay, now these lambda values, notice how in elastic net it has two lambda values. Here, you can essentially control whether you want this constraint to be more important or this one to be more important. Okay, so unfortunately, there are many ways to say the same thing: adding a constraint, regularization, adding a penalty. All three things are used pretty equally, and therefore you need to know what all three means. Constraint is the same as penalty, is the same as regularizer. Okay. Next, let's better understand this separate topic really quickly, and that is the weights of linear regression, weights. So let's say we have this data set, and given these three proteins, we want to predict the percentage of somebody getting cancer. Okay, now after we use linear regression and we solve the weights, it turns out that the first weight is 7, 6, and 0.00001. Okay. This implies that when you multiply the weights by the data, like kind of like this, it will give us the prediction. Okay. So the idea here is that we have these weights, and the weights, when you multiply by the data, it gives us the prediction. And when we do that, if you look at the weights really carefully, can you say, can you identify which protein is more important in terms of its impact on the final solution? Well, if you look at this multiplication, because of this value is so small, the third protein really doesn't matter. It doesn't matter what value you pick, right? Whereas the first protein is quite important. Therefore, what this is telling you is the third protein, the values really doesn't matter and has very little impact. The weights, the weights of the linear regression actually give us a lot of information. Previously, we only care about taking the data, pass it into a function, and predicting the label. Okay. So that's what we've been doing, predicting a label. However, if we just look at the weights themselves, it actually gives us a good amount of information, specifically how important each factor is that impacts the final decision. Okay. Once again, this observation tells us that the weights of the linear regression not only give us the function, it also tells us how much each feature contributes to the final prediction. So this is very interesting because now after you solve regression, linear regression, you will not only be able to make predictions, you will also be able to tell which factors contribute most to the predictions. And this brings us back to the three algorithms we have. The constraints we create, right? We were talking about constraints before this. It creates a compromise solution, right? So, but when do we use L1 norm versus L2 norm or elastic net? Right? So let's take a quick example. And below are the three results. The first one is from linear regression, L2 norm, and L1 norm. So we solved it in three different ways. And this is a true solution. So let's say this is the solution. Notice how if you just solve regression, it does a pretty good job of reaching the true solution. Okay. Now, if we solve it with L2 norm, as expected, it's trying to find a solution with notice how the accuracy rate is pretty good, but with weights that are smaller. Okay, so it's a smaller weight. However, in the third example, when we solve it with the L1 norm, notice that the accuracy went down a lot. Now, you might be thinking to yourself, why would we do this if the accuracy is hurting so much? And the reason is because L1 norm has the power to push the non-important features towards zero. It does a very good job pushing them to zero. And therefore, it allows you to weed out features that are not important. Okay, so notice the zero. So L1 norm is very, very useful for identifying important features. And that's why the L1 norm is sometimes preferred, um, even though it's not as accurate, right? Notice how L2 norm is really accurate. All he did was basically lower the numbers a little bit. Okay. Now, this is why elastic net comes in. Elastic net allows you to control the difference, the importance between L1 norm and L2 norm because elastic net has both, right? So you can control WL1 and WL2, lambda 1, lambda 2. Depending on what you pick for lambda 1 and lambda 2, the elastic net allows you to like fine tune how much you want to like push non-important factors to zero. Okay. All right. So these lambda values, as I told, has a name. They're called hyperparameters. And they are basically things that you need to set even before you start training. You just need to pick a number for them, and the number you can decide. Now, now, if you don't know what the number you want to pick, you could also use model selection to do it. So basically, let's say you pick a set of numbers. You want lambda to be possibly 1, 2, 3, 4, 5. So 5 possibilities. And what you do is you follow the train, validate, test for every single possibility. And then once you figure out which one of these work really well, then you'll pick that one. Okay, so that's another way to pick these hyperparameters. That you treat them as different models. Okay. All right. So at this point, I want you to put everything we learned so far together. Um, this is going to be a pretty good size project given the data above, right? So here's the data, and this is the feature map. So it's a polynomial. Identify the derivative. So you're going to try to do a lasso. So you want to find the derivative of this, and then put the derivative in matrix vector form. Okay, put it in matrix vector form. It's important that you can do this because this will just make your life so much easier later on when you're coding. And then start off by seeing if you can write the Python code to just run one gradient descent step, just one step. Once you can get that one step, make sure you got your answer correct so you can run one single step. Then put it in the loop to basically minimize the objective and solve this problem. Okay. As you do that, lastly, I want you to plot out the gradient descent steps. I want you to show that as you take each step, it kind of goes lower and lower. Okay. Now, this I actually wrote the code. I wrote the code to show you guys what it looks like. So this is with the lasso objective, and this is what it looks like. Let me see if I can find it. I think it's over here. So the lasso objective. I think it's right here. No, this one. Okay, so let me play the video for you. So you can see that initially the line is not doing very well. And as you run gradient descent little by little by little with the lasso objective, the line is just doing like fitting this data a little bit better, a little bit better, a little bit better. You can see this. Okay. Of course, this takes a while. So let me see if I can fast forward. Notice how as I fast forward, it does better and better and better. So, so anyways, that was 4 hours of my life writing this that I'll never get back, but worth it. Okay, so let's go back to the lecture. So, as I said, right now, this is I want you to pause the video and see if you can do this. This basically puts everything we've learned this semester together into this like neatly package. Okay. So, and I have provided the solution here. You want to make sure you study the solution. This is the part where you do the conversion from the derivative in like the summation format into this like matrix vector format, and you want to make sure you can do this as well. So I also provide a solution to this is the solution after you run one step of gradient descent. Over here is the solution where you run multiple steps of gradient descent. Okay, so these are the multiple steps. And you notice how the error keeps decreasing. Okay. Okay, I think that's that. Okay, I've also created the Python code that generated this plot because, well, generating plots are nice. This you can look over yourself how I did it. Now, when I generate the plot, I first created the linear regression model. That's the black one, which I then plot them as black. Now, when you want to run the polynomial, remember to run polynomial, all you have to do is do the polynomial feature. You run the polynomial feature, then you run regression on the polynomial feature. Okay? Ridge regression has its own. So this right here is ridge regression. So all of these are sklearn library. These are library functions where you don't have to run it from scratch. Of course, for your homework, I expect you to run everything from scratch. But when you're actually working for a company, you can essentially just run these code. Okay, so more specifically, this right here is linear regression, right? And then you can call the ridge regression this way, and you can call the lasso this way. Okay. All right. So why are constraints so important? The world peace objective. Let's say you want to find a function that minimizes war, which is a very, very noble pursuit. However, notice how majority of the machine learning are trained through gradient descent, and gradient descent doesn't care how you achieve the final objective. And this is very, very important to understand. And it's the reason why machine learning is dangerous, because since the machine learning algorithm doesn't care, it may tell you the best solution is to simply kill all humans, which will be true. If you just kill everybody, then you will end all wars. And because gradient descent doesn't have the same values we do, it can come up with any solution as long as it satisfies the final, right? So even if you add constraints, you still have to be very careful. Like war, you want to minimize war while not killing humans. Well, constraints can't guarantee our safety because machine learning algorithms can come up to say, well, if you kill all the food supply, that will end all wars, or you remove the sun, right? None of these, according to the machine learning algorithm, is directly killing a human, right? And this is why machine learning uh, algorithms could be really dangerous if we don't use them properly. Okay, and this is why constraints are so important. All right, so another example of constraints. So when I was working as a researcher, we looked into essentially predicting a gestational age when the baby comes. And I had to add a bunch of constraints, right? For instance, when the baby are born too early, 37 weeks, right? That's basically the threshold of when it's premature. So so this is the underlying fact, and then we add the constraints knowing that the range of the possible ages should be between 22 and 43. Okay, which means that we know the predictive range. Like if it's below 22, it doesn't make sense. If it's more than 43, that doesn't make sense as well. So I was able to create a constraint that looks like this. Now, remember what ReLU does. The ReLU function essentially says if it's positive, then it gives you a value. So notice how if my prediction is greater than 43, then it gives me a positive value, which during the minimization will try to minimize. Therefore, this right here is acting as a constraint because you don't want any numbers greater than 43, right? You want a less than 43. If it's less than 43, then ReLU will turn it into 0, implying that your minimization is working well. In this example, I I'm making sure that 22 minus my prediction, right, is is how I constrain the solution to be above 22, right? If this is below 22, think about it. If yi is below 22, this will be a positive value, and ReLU will treat the positive value as a positive value, implying that like this right here becomes a constraint. So this is only not a constraint when yi is larger than 22. So these are the examples of like constraints that I have used in real life. All right, so one more example, the Horvath clock. As a hobby, I study the biology of why people get older, just for fun. And in 2013, the Horvath clock was discovered. And the idea is pretty simple. We all know people that sometimes look older or younger than their actual age, right? And therefore how old a person how many years they've actually lived may or may not be indicative of how old they are biologically. So you can think of people with chronological age or biological age, where chronological age is how long they've lived, and biological age is how much damage essentially their body has sustained throughout their life. Okay, so the idea is, can you we know how old a person is through their birthday, but can we measure how old a person actually is biologically? Okay. So the idea is, what if we collect the various genetic data for a person, but not about their genes, more about the pattern which the genes turn on and off. Okay. So the theory is that if you're younger, your genes turn on and off with a certain pattern. And when you're older, you will turn on with a different pattern. And the label was the age of the individual. So it turns out that it turns out that if you use this as the data, it does a really, really good job of predicting a person's actual age. Like really, really good job. And as a result, like it gives us a strong indication that how old we are is essentially just like patterns of our genes turning on and off, changing throughout time. Okay. And guess what? With this algorithm, they ran it using elastic net. Elastic net. So it was elastic net. A pretty simple algorithm was able to essentially achieve this. Okay. Now, at this point, we've already discovered a lot of things we could do to slow down the biology of aging, such as regular sauna use, regular exercise, don't sit around all day, eat less, make friends, reduce stress, sleep, put sunscreen on. So all these things actually have been studied, and these are all the recommendations if you want to slow down how quickly you're aging. Now, for more detail on the article, you can read it here. In the future, I think it'll be really fun for us to reproduce this work. I think this will be very fun. Okay. Now, if you're interested in doing research into this article to help me basically reproduce this work, let me know. All right. So I think this is it. So for your final exercise, once again, let's pull out the stock prediction data. And then we already did the train validate split. We did this in the last class. And then you also did the pre-processing. Now, what is different this time? You want to perform second or maybe higher, like third or fourth order polynomial. And this time you want to add a constraint. One for Lasso, other one for ridge regression. Okay. That's basically the only difference. You can basically take your code and see if you can achieve it. Run it three ways using gradient descent yourself, your own, and then with the SK library, and then use the validation data to identify the ideal lambda value. So remember, you when you have regularizer, you add a lambda value in front of it. So you want to test it out to see like what lambda values make sense when you do the validation. Okay. So I think that's it for today. I will see you in the next lecture.